So, we continue with our discussion on clocking and timing issues in flip flops and synchronous sequential circuits. So, the title of this talk is clocking and timing in the second part. Now, in this part we shall be talking about several other features of timing that are important. For example, we shall be talking about the maximum clock frequency that you can use in a circuit such that correct operation can be guaranteed. Then we shall be looking at something called hazards and clock skew, already we have mentioned, and finally, we shall be looking at an example synchronous sequential circuit and see how it works. Okay. So, we consider this example, means a very simple example. Now, see, means any synchronous sequential circuit, generally if you look into the block diagram level, it will consist of two blocks. One is a block which contain one or more flip flops, and there will be another block which will be a combinational circuit, just gates, combinational circuit. So, the output of the combinational circuit will be feeding the flip flops, and the flip flop outputs can come to the input of the combinational circuit. Now, in addition you can have some more inputs coming here and some outputs can be generated from here. Now, in the example, any of course, means clock will be there, clock will be applied to flip flops. And now in this example we do not have these inputs coming to the combinational circuit and these outputs generated from the combination circuit. So, for flip flops we have a single D flip flop here, and for the combinational circuit we have a single inverter or a NOT gate here. Okay. So, let us look into this example and try to do an analysis. Now, the assumptions regarding the delays that we make are as follows. We assume that the delay of an inverter, this NOT gate TP inverter INV is 2 nanoseconds. The delay of this flip flop, so once the clock comes, after how much time the output will come, it is 5 nanoseconds TPFF, and setup time of this flip flop is 3 nanoseconds. Now, as I said earlier, if you recall in our last lecture, the hold time and the propagation delay overlap. So, actually hold time need not be considered when you are talking about the maximum clock frequency, minimum clock frequency, minimum time period. Yeah, fine. So, let us see. For this example, as we had said, now we are trying to determine the minimum clock frequency for which the circuit will work correctly. Let us look into the clock. The clock signals is coming, I am just showing two pulses, positive edge triggered. So, this is the active edge. So, if we look at the second edge, let us concentrate here. So, with respect to the first edge, so when the first edge comes, so after how much time this D will be generated? There will be a delay out here which will be equal to the delay of the inverter, the inverter delay D will be generated, and after this delay is generated, you will have to hold this before the clock pulse also. Before this clock pulse, you must have a mandatory setup time, this delay you have to give, and also you should not forget the delay of the flip flop. So, after TP inverter you are generating this, now after this delay this will get into this. So, there will also be a propagation delay of the flip flop. So, these 3 delays are getting added up here and they must be greater than the clock time period. Let us take 2 cases. So, what I am saying is that T mean in this example will be sum of these 3 times, which is coming to 10 nanoseconds, 2 plus 5 plus 3. Now, because frequency is the reciprocal of the time period, the maximum frequency will be 1 by minimum time period. So, 1 by 10 nanoseconds, 1 by 10 nanosecond means 10 is 10 to the power minus 9. So, it is 10 to the power 9 by 10, this is 100 mega, 10 to the power 6 is megahertz, right. Now, let us say suppose we choose a clock with time period 9 nanoseconds. So, what we have to do when you are designing a circuit, we will have to make this calculation and see that whether 9 nanosecond is enough or not. In this case, because we see that we need minimum of 10 nanosecond. So, this will lead to a timing violation. We cannot have a clock with time period 9 nanosecond. But let us say we are using a clock with 12 nanoseconds or 15 nanoseconds. This is certainly greater than this minimum of 10. So, this is perfectly permissible. So, what we do, whatever minimum we calculate, in addition we also put some more, you can say, buffer. So, if it is coming to 9, we say that well, let us keep it minimum 10, and that way we can choose the clock frequency, maximum clock frequency with which you can operate our circuit, right. Okay. And one thing to note is that, as we had said, that for a hold time delay does not affect the calculation here, because when the clock edge comes, hold time means after that minimum how much I have to hold the inputs, but already that propagation delay is calculated from the clock edge. So, propagation delay time includes the hold time. So, we need not have to add the hold time again. Okay. So, this does not affect the calculation. Well, let us take another example, which let us draw like this. Suppose we have a D flip flop, let us call it D 1 and Q 1, this input is coming here, and let us say in Q 1 this is being fed to a, let us say, chain of gates. So, here I am showing 3 gates, let us say. So, some external inputs are coming here, some external inputs are coming, let us say this Q 1 itself can come here again, and this is being fed to another D flip flop, let us call it D 2 and Q 2, and there is a clock signal which is being fed to both these flip flops. Consider a scenario like this and assume that the propagation delay of a NAND gate TP NAND is 3 nanoseconds, propagation delay of a flip flop is 5 nanoseconds, and setup time is also 3 nanoseconds. So, for this circuit, if you just look into the timing once more, so I am showing 2 clocks, let us say like this, these are the active edges. So, if I look at Q 1, when the clock edge comes, the propagation delay is 5 nanosecond. So, q 1 whatever it was earlier, I do not know whatever it was earlier. So, after a delay here of 5 nanoseconds, I will get the value of q 1 here after this clock edge comes TPFF, right, and this value will remain after that. Let us say does not change after, let us say. Now, let us talk about D 2. What will happen with D 2? D 2 will also face the delay of these 3 NAND gates, which will be equal to 3 into 3 9. So, there will be another delay of 9 nanosecond after this. So, D 2 whatever the value it was, I do not know. After that whatever is the new value of D 2, new value of D 2 will be generated here. And in addition, before the next clock edge comes, so you must have the setup time of 3 nanosecond maintained here. So, 5, 9 and 3 are the minimum time that you must have between 2 successive clock edges. So, in this case your minimum time period will be 5 plus 9 plus 3, which is 17 nanoseconds. So, in this way, given any circuit, so if you have an estimate of the delays of the different components, the gates, flip flops, then you can have a calculation which can tell you what is the maximum frequency with which your circuit should work. So, you should not blindly select a clock frequency and see whether this circuit is working or not, because every circuit component will have some delay and the clock must be slow enough, so that all gates are getting sufficient time for evaluation. Okay. So, these two examples actually try to show this. Now, talking about clock skew, already I just mentioned this earlier in the last lecture. The main concern is that the clock signal, let us say suppose we have a chip here as said, the clock signal may be fed to the input of the chip and there can be several flip flops spread all around the chip. So, this clock signal has to be connected here, has to be connected here, has to be connected here, here and so on. So, the length of the wires will be unequal, and because of resistive and capacitive effects of these wires, there will be delays, RC time constant delays, and the delays will be unequal in general. And this due to unequal propagation delays along the various paths, there will be clock skew, which means clock signal may not reach all the flip flops simultaneously. Well, of course, when you are designing this clock network, we try to reduce clock skew as much as possible, ideally 0, but in practice we cannot exactly make it 0, we try to reduce it as much as possible. There are methods of doing that, but that is slightly beyond the scope of this course. We shall not be discussing how to reduce skew here, just what is skew, that is enough. Now, the point to note is that let us assume T skew is the maximum possible clock skew, meaning for 2 flip flops, if let us say the clocks are coming, the first clock is coming like this, the second clock is delayed like this. So, what is the maximum difference? That is defined as T skew. Okay. So, if we consider also clock skew, then the minimum time period for the clock, the calculation would be a little different. Like as we had seen earlier, for the T min calculation, we have to calculate the delay of the flip flop. We calculated the delay of the combinational part, that means the 3 NAND gates were there in the previous example, and of course, the setup time. Now, in this case, in addition, we also have to add clock skew, because we do not know how much clock skew is, but we know what the maximum clock skew can be, which means for the second flip flop the clock edge might get delayed or might get advanced by that amount. So, that also you must make provision when you are estimating the minimum time period of the clock, right. Because of this, the clock frequency can reduce with respect to the case where you are ignoring clock skew, right. This is the idea. Now we consider another property of circuits related to delays. These are called hazards. The idea is, given a circuit, I am applying some input, I am expecting some outputs. Let us say the output was 0, now the output is supposed to be 1. It may so happen that instead of the output going from 0 to 1 in a clean transition, we may say that it may vary several times before settling to 1. That means, there can be unnecessary transitions for very short durations. These are called glitches, and these glitches actually are called hazards in circuit design. So, definition of hazard very loosely can be mentioned as that they represent momentary transition in the value of a signal line to the opposite logic value. Like I am showing some examples. Two types of hazards are possible, static and dynamic. Static hazard is one, it says there is a momentary transition when the initial and final values are the same. Like the initial value was 0, final value is 0, but what I see in the output that it makes a momentary transition to 1 before settling to 0. That means, 0, 1 and back to 0, or the other way around. Suppose the output value is supposed to be 1, it makes a very temporary transition to 0 before settling to 1. Dynamic hazard is similar, but here the initial and final values are different. So, let us say initial value is 0, final value is 1. So, it may so happen that instead of a clean transition, it makes a transitions like this and then settles down. That means, 0 to 1, back to 0, again 1, or the reverse from 1 to 0, back to 1, like this, 1 to 0, 0 to 1, 1 to 0. Now, if the circuit outputs are directly connected to some other circuit and these glitches may affect the operation of those circuits, then there can be a problem. So, you should be aware of such glitches or hazards and design circuits in such a way that it should only be activated in the edges of the clock, and these hazards should be stabilized before the clock edge comes. Okay? So, the idea is like this. So, let us take some examples to illustrate the occurrence of such hazards. So, here we consider one example like this. This is a circuit comprising of 4 gates. Let us assume delay of the NOT gate is 1 and delay of the other gates is 2, 2, 2 and 2. Let us show a typical scenario. Suppose this this input signal A is applied constant 0. So, we have applied a constant 0 here. B is also constant 0, B is also constant 0, 0. Now, S what we do? S, let us say it was 0, here we make it 1 and then we leave it as 1. So, what will happen to S prime? S prime is the NOT of S and the delay of this NOT gate is 1. So, it will be NOT, but it will not become 0 immediately after a delay of 1. So, these grids I have shown, these are 1 unit. So, after 1 unit S bar will become 0 and then it will remain 0. So, now if you calculate f, what will be the value of f? So, in one case you are taking OR of A and S, OR of A and S, the delay is 2. So, here 1 2 delay 2 means here this point will become 1 at this point. And if you look at this gate, OR of S bar and B, S bar and B, you see S bar is 1 here, right, or B. So, it will get again delayed here. So, if you just plot this, this will become like this. This I suggest you also show the waveforms of these two lines and then do an AND, it will be clear to you. So, here what you are seeing is that the f was 0 and it is supposed to be 0 again in the stable state, but because of the delays of the gates it is temporarily moving to 1 and remaining 1 for one time unit before coming back to 0. This is an example of static hazard. Right. Let us take another example. This is a slightly more complex circuit. Here we assume that delay of the NOT gate, there are 3 NOT gates is 1. So, this is 1, this is also 1, this is also 1, and NAND and NOR gates, there are 4 of them, it is 2, this is 2, 2, 2 and 2. So, here again let us take a scenario where the input A is permanently at 0, I am applying 0 at A. B input, let us say it was 0, we make it 1 here and leave it at 1. C input, let us say it is 1 continuously, it is 1. These are the 3 inputs A, B, C you are applying. Now, let us see what will be the value of x. You see the value of B is getting inverted twice, 2 NOT gates. So, the same value should come at x, but after a delay of 2 units 1 plus 1. So, whatever B is there, there will be a delay of 2 . So, x will be like this, right, B after delay of 2. And what will be y on the other side? See here this A is 1, A is 0, B is also becoming 1. So, if this is 1, this is 0. So, output of this y would be 1. So, initially y was 0 because A 0, B 0 both were 0, it was 1 0. So, it was 0, y is supposed to become 1, but the delay will be from the inputs 2 plus 1 3. So, when B is changing after that 1 2 3, so y will also change, but it will change here after a delay of 3. Now, if we just look at f, I am again jumping some steps, you can also plot the value here, it will be, it may be easier. But what we will see that in f, in this part of the circuit, say after this x has come, there is a delay of 2 before this is changing and again a delay of 2 before this is changing. So, 1 2 3 4. So, you will get a value like this, B is changing, yeah, like this. So, the first edge will be because of this transition in B, you show it like this in an arrow. This second edge will be due to transition of x here, this edge, and the third edge will be due to the transition at y here, this. So, you see all these edges are because of the delays in these gates and some signal value changing somewhere. This is an example of dynamic hazard which we have demonstrated. So, we are not going into any theory behind static or dynamic hazard, just I have shown you one example, and with the help of the example we have seen how this hazard shows up. Okay. Lastly, we shall be showing you one example of synchronous sequential circuit. This is an example of a serial adder. Now, before going into a serial adder, well, earlier you have already seen how a parallel adder works. Like let us say, whenever you add two binary numbers, let us take another number 0 0 1 0 1, you add these bits, accumulate the carry, add this carry, carry, carry 1. This will be the sum, and initially for the first stage you typically assume that the carry is 0. So, in the parallel adder design we had a full adder in all the stages. Now, what I is saying is that we are saying we have a serial adder, that means I want to design a circuit like this, where these two numbers, let us call it A and B, they are fed serially. Serially means least significant bit first. First I feed 1 and 1, then I feed 1 and 0, then I feed 0 and 1, then I feed 1 and 0, then I feed 0 and 0. And in the output, here I am expected to generate these bits in that same order. First I will get 0, then I will get 0, then 0, then 0, and finally 1. So, there is a single input A, single input B, where I am sending one bit at a time, and in the output I am generating one bit at a time. So, if you think that how this circuit should work, suppose you are a serial adder, you just imagine yourself to be a serial adder, where the bits are coming one by one. So, if I tell that well the next pair of bits are 1 and 0, what should be the output? Well, your question will be, well, I cannot say what will be the output unless I know what is my carry, because I also have to add the carry, right, to A B to get the next sum. So, you will have to memorize the carry. There has to be a flip flop inside your circuit which will be memorizing the last carry, right. So, to implement this circuit, well, we shall be going into the formal way of designing such circuits later, but what we are saying is that we shall having a D flip flop, and what we will do, we will be having a full adder, where the two serial bits A and B will be fed here, and the carry input will be the output of this memorized carry will come here, and the output of the full adder, the carry out will be stored in the flip flop, and the sum will be generated as the serial output, and this will be working in synchronism with a clock. And the only point to note is that this flip flop must be having an asynchronous clear input, because we have to initialize Q to 0 before you start the addition. So, every time you add 2 bits, the previous carry will be coming, those 3 bits are added, you generate sum, you generate a carry, the new carry gets stored and the process continues. So, you see the advantage of a serial adder is that you need so little hardware, you need only one full adder and one flip flop, but the drawback is that if you are adding to 16-bit numbers, you will be requiring 16 clock pulses. So, it is very slow serial. So, we have just shown one example, later on we shall be looking into more formal ways of designing or synthesizing a circuit given a specification. This we shall be starting from our next lecture onwards. So, with this we come to the end of these lecture. So, over the last 5 lectures we discussed various latches and flip flop types and clocking and timing issues. Thank you.